So we're going to be talking about experiment 7. Experiment 7 is and this experiment the, and we make predictions. We expect zinc to be able to react with some of these things. Sulfuric acid, copper sulfate, and silver sulfate, copper, sulfuric acid, zinc sulfate, place for us to put relations and what's the reaction? Some titration data that's going to take in we do the same experiment twice. And this balanced chemical so manganese react with concentration. So you're going to experiment data determine what that percentage is. Now, remember that you have to do this for the original solution. So it got diluted before it got used. So let's multiply that up. The other thing is that we are expecting that your hydrogen peroxide is 3%. Because that's what the bottle says it should be. It may be, it may not be. That's okay. We're going to figure out what it is. So that's that. So, and all of this information should be based on the selectable series. So anything that's on the left-hand side of this line should be able to react with anything that's on the right-hand side of this line. So if zinc is here, in theory, it should be able to react with anything currently. So that's how you should be able to base your predictions here. One thing that you need to be aware of is when we talk about the H2SO4, you're looking at what it reacts with H2. Okay, that's what we're talking about. There's 4 H plus in this. So H2, copper, sodium, and sulfur. So expect them to react. And we do that for zinc and then for copper. So base your predictions on what you've seen in this electrolyte series. Then you're going to look at some of this data. So data that's here. And what it says is that zinc metal with sulfuric acid does have a reaction, and there is no information for that. Now, there is also available to you something that should use. If you go to experiment 7, you'll see that there are. So for experiment 7, you'll see that there are 2 simulators. So there's an activity series simulator that takes you to this. You can set this. So we're looking at zinc as your metal, and then you can set this for whatever silver, and you can watch that this reaction actually happens. The silver comes in, the zinc goes out. So that's what we're looking at. So we expect that to be react. So you can make your own observations based on these. Between this activity series and the cell simulations, you will have enough information to be able to the hydrogens. This one you cannot do in the activity series because the activity series simulations are based on metals. But you need to be able to look at this and say, okay, is this actually going to happen? And what you're looking for is, are you getting this thing to do what you expect it to? So we can, because we know from the silver one things are actually happening. So 2 plus. So now I know that that's what I'm expecting. And the HG plus goes to the G. So then I can look at the things that I don't have. And what I see here is it's coming off as 2 plus, and we're firing bones. So that's why those two is from. So those simulations should be able to give you all the information you need to be able to make your own observations. I would prefer to make your own. But if you are not comfortable with that, or if you're doubting yourself, here is data about what should have been. So this is kind of like having me in the lab to go, is that what I think it is? Yeah. Okay. So this is what you can see. But this way you're able to do your own type of experiments. All right. So those are observations. Did you observe a reaction based on the observations that you had? Okay. This titration data is down here. So the KMNO4 is listed because you'll need that to do your calculations. And then all the volumes that you need are here to get the best sample initial KMNO4. That nice. Okay, that's supposed to have a number in it, but give me a little bit and I will get you some numbers for that. We should have numbers in it. So sorry. Some potential values. But you would fill in the volume of the diluted sample. So what is the volume that you had for that solution? So you make each of these make each of these samples per the prepared titration, obtain 60 mils of 0.02 km. It says in a small beaker, obtain 10 mils into a 100 flask. So you do a dilution of that. So your M equals 10. Supposed to be. So this is the actual value that should be here. It's roughly 2%. Sorry. M1, we have our V1 equals 10, our 2 equals 100. And so M2 is going to be 0.01 times that value that you have. And you're going to be able to calculate what this M2 is based on the amount of the KMNO4 that you add. So once you've done that calculation and you calculate what the M2 is, then you have to go backwards. Remember that you need to multiply by 10 to get that original concentration. Okay, so don't forget about that part. And then you want to calculate the percent error for that. So give me 2 seconds. So data that I would put from what we have here. So the volume of the diluted sample is 10 mils. My final volume is 100 mils. My initial burette reading is 8.4. And this one is 4.6. The final burette volume is 28.1. This one is 24.7. So the volume of the KMNO4 that you used is the difference between those two. Okay, so you calculate that difference. And then the mass percent of the H2O2, you're going to calculate. Now, mass percent, how do we define mass percent? It's the mass of H2O2 over the mass total. Okay, so we have a density for this particular, so a mass, or sorry, we have a mass for our sample, that's 1.01. And once we calculate the mass of H2O2, which we can do through this calculation, then we can calculate a mass percent. So that percentage is what you're going to be comparing once you've multiplied by 10 to this 3%. So don't forget to do that, to multiply it by 10 to get it back to the original type concentration. Okay. So that's what we're looking at there. So that should be everything that you need. So again, 28.1 minus 8.4, and that gives me 19.70, 19.7. So that's how you're going to get that. And the mass percent of the H2O2, this is supposed to be 3%. That comes from the bottle. And this calculation, the mass percent, is what you're going to calculate to do this. That is something that you'll need to do with the data that you have. Now, how are you going to do that? Well, you're going to do that using stoichiometry. Okay. So if we look at the stoichiometry for this, we have to balance the redox reaction, right? Once that is balanced, then we can look at what is the volume. So I will take my volume of KMnO4 and we'll divide that by the molarity of the KMn. Multiply by, see my units. Multiply by the molarity. So if I multiply volume times the molarity, I get the number of moles. I then need to use the molar ratio. So this will be the number of moles of KMnO4 from my balanced equation. This will be the number of moles of H2O2. Make sure that you do that. Once you have moles, you can divide by your original sample volume, which here is 100 milliliters. And of course, you'll need to convert that to liters. And actually, you don't need to do that because you don't want molarity. So they ask for mass percent, you want a mass. That calculation should give it to you. So the multiplication of the volume in liters times the molarity, and then use the molar ratio to get the correct mass of the, and that will give you the number of moles of H2O2, and you can divide by the molecular weight of H2O2. Oh, I won't divide again. I'm doing units in my head. Sorry. I do this a lot. So multiply by the molecular weight in grams per mole. And cancel. Okay. So that's what we're looking at there. So that should give you the mass in the diluted sample. Remember to multiply that by 10. And then this is what I would put there. So that mass percent. Which again, this answer divided by mass of the total, which is that 1.0. Information that they give. Okay. So that's that. Again, I don't think it's that bad. Make sure that you've done your balancing on your equation. And that's everything for that page. We then go into your summary. And of course, if you're looking for our summary, our objective is so much pages. It's like 46. Balanced redox reaction, and you did this already in your notebook. So this is what we were just talking about, that balanced redox reaction. So this thing says, assuming the density of the diluted H2O2 is 1 gram, we'll calculate the mass of each aliquot used in the titration. We actually have a mass, so you can just put this right here because that's what was given to you. Okay. Use stoichiometry and the balance reaction above. Calculate the H2O2. So the calculation that we just talked about doing is going to go right there. And you're going to do it for trial 1 and trial 2. The sample titrated was diluted by a factor of 10. Calculate the mass of H2O2 in the original bottle. And then put your data into the table that we were just talking about. So this table right here. So yeah, that's what's going to go in that little box right there. Okay, so that's what we were talking about. So that's that part of it. Note the percent H2O2 on the bottle. Calculate the percent error. Again, percent error is the absolute value of actual minus theoretical over theoretical. And it's that expression times 100. Your actual is the number that you calculate. The theoretical is the 3%. Were your results accurate? What do we mean by accurate? Well, how close is your calculated value to that 3%? So how close is it to the real value? That's what accurate means. Were your results precise? Well, how well do they agree with each other? You know, are they good values, i.e., do we have good agreement between the two experimental things? And that's a judgment call. Just make sure you explain to me why you chose what you chose. Provide some source of error that affected the accuracy and precision. There are a number of things that can affect that, things that I can think of offhand. Improper dilution. So if you didn't dilute the thing, improper reading of the burette while you're trying to take the initial and final volumes. Improper storage of the H2O2. It's been exposed to light. Those kinds of things. So think about it. As long as you have explained why it's an issue, that's what I need. Why is it necessary to store H2O2 in a dark bottle? So think about that. I'm not going to tell you. You can Google it if you really want to, but I want to know what that has to do with anything. Okay? And that's for you to figure out and explain. Okay, because I want to see what your logic is for whatever you tell me, because you could tell me any number of things. So I want to see your logic for that. Now, the other thing, where's my post lab? I gotta find my post lab. Where did I put it? So, okay. So here's your post lab. Right, the 4 net ionic reactions. So anytime that there was a reaction, you'll see that there are 4 of them. Write the net ionic reaction for those. How many did you predict correctly? Well, however many you did. That's great. If they weren't correct, do you understand how you misinterpreted the electromotive series? So now that you know what it's supposed to be, can you look at that electromotive series and tell me why you guessed wrong? That's what we're looking for. You're supposed to figure out how to use that electromotive series to get it right next time. We need to consider Ag, Cu, Na, Zn, and H, and put them in order of relative reactivity. Now, that's supposed to be based on this. So those you will find in here. Okay. The next part B, it says consider SR. Now, SR is not in here, all right? But we're asking you to put it in this list based on stuff. Okay, so I need you to look at your periodic table, figure out where that is in relation to other things, and figure out where you think it would go in that list. It doesn't matter if you get it right, I don't care, but you have to put it in there and explain why you put it where you put it. Okay. Use the electromotive series to decide if a reaction would occur between each of the following combinations. So Al metal, we're talking about Al here and Ca2 plus. So Ca2 plus. Do you expect that to work? Okay. Fe3 plus and ZnO. So Fe and Zn. Okay. HCl and Ag. So HCl is here, Ag is here. Would you expect that? H2SO4, which is again this H2, and K, which is here. We expect that to be reactive. Sorry, distracting myself by reading. I'm trying to teach. It's not useful. Okay, so use this and use this information to explain to yourself how this should work. Okay. Out of A and B, only one of those should happen. Out of C and D, only one of those should happen. That's the one that you need to write the net ionic reaction for and tell how many electrons are in each of those. And then consider the titration reaction. What's the oxidizing agent? So what causes oxidation? So what is reduced? What is the reducing agent? I.e. what causes reduction? And how many electrons are being transferred in that? Okay. So that's that. And I think that's it. Yep, that's the end of it. So that's everything for that. Okay. Now, again, I would expect that you should be able to look at this and say, okay, how does this work? And one of the ways that I would do that is I would come in and I would look at this activity series, and I see that Zn is to the left of the Cu, right? And it says that this reaction occurs spontaneously, right? In this process, the two half reactions are the Zn going to Zn2 plus and the Cu2 plus going backwards. So, i.e. going to the solid. So would you expect the Al metal to react with the Ca2 plus? And based on where it is, it's to the left. I would expect that to be true. Okay. Fe3 plus and Zn metal. Again, Zn is to the left of the Fe. So expect it to be able to react with the ion. H2SO4 is going to be the 8. So the H plus is what we're looking at, the ion of the H2. And H2SO4 and K. So can K react with that H plus? And the answer there should be yes. And HCl and Ag. So if you're talking about the ion here and the Ag, would you expect that to? So 2 of those work, 2 of those don't. Tell me which ones they are and write me a net ionic equation. Okay? So that's what we're talking about for that. That takes us through experiment 7. And I hope that that answers all of your questions and shows you where that data should come from. Again, I would use this as a double check. I would use the simulators to do this to see what you get. Make those combinations, see what you get, and then verify against the data that you've been provided to see if that's what you would expect. Okay? It's okay to get it wrong. It's absolutely okay to get it wrong, but why did you get it wrong? Figure out what it is that in your process that didn't work. Okay? So that's everything for experiment 7. So I'm going to be done with this recording. I'm going to stop and end the meeting, and I'll talk to you soon.